Welcome to this class on fluid mechanics, where we will continue our discussion on the exact solutions of Navier-Stokes equations. In the last class, we had seen that if we have flow between two long and wide plates of the dimensions which were shown, and if this flow is caused by a pressure gradient, then what we got was the velocity profile of the flow. The expression turned out to be Vx is equal to minus P prime upon 2 mu into h square minus y square, where h was the half height of the channel and P prime was equal to P2 minus P1 divided by L, the pressure gradient in the x direction. So this was the expression which we got for the velocity profile. And using this expression, we can then get the flow rate. Flow rate will be equal to integral Vx dy from minus h to h. And we can also get the shear stress on the plate. Shear stress on the plate, if we look at it, the plate, let's see how do we find that. The plate is a y face. So the shear stress on the plate will be tau yx because the flow is in the x direction. And when we look at our sheet, tau yx is equal to mu times partial Vx by partial y plus partial Vy by partial x. And these we substitute from the expression of the velocity profile, and they have to be evaluated at y is equal to h or minus h. And using these, we can calculate the expression for the shear stress on the wall. Now, one thing you can see is, before I move on, that this expression, if we look at it, if I try to use the integral flow analysis, let's try to see if there is a link. If I use the integral flow analysis and I use a control volume as shown, and here we have flow coming in, flow going out, and now if we want to find the expression for shear stress on the wall from integral flow analysis, then what you will have will be sigma fx is equal to d by dt of integral vx rho dv plus integral over the control surface vx rho v dot n dA. This is the integral momentum equation in the x direction from the integral flow analysis. Now what you will realize is that since the flow is steady, d by dt term is equal to 0. And in this flow, if I call this as surface 1, outlet as surface 2, and surfaces 3 and 4, then what you will realize is that these terms are not equal to 0 on surface 1 and 2. And because the flow is fully developed, this will imply integral on 1 Vx times rho v dot n dA. This will be equal to minus the integral upon 2 Vx rho v dot n dA. And this is because v dot n dA on 1 and 2 are opposite. One is plus and the other is minus. So therefore, the second term also becomes equal to 0. And what we get is sigma fx is equal to 0. Now what is sigma fx? Is the surface forces in the x direction. So on this control volume, let's draw this control volume here. sigma fx will be, there will be two contributions, one due to pressure and the other due to the shear stress. So on, and we have to calculate all this. So on surface 1, the x direction forces will be equal to P1 times A1 in the I direction, which is equal to P1 times 2h times W in the I direction. On surface 2, this force will be minus P2 A1I, and this will be equal to minus P2 into 2HW into I. Now on surfaces 3 and 4, let us combine. The total force will be shear stress multiplied by the area. Area will be equal to L times W times 2. And this will be in the minus I direction. So shear stress on the wall times L times W times 2 into minus I. So now when we equate all these, what we get is P1 minus P2 into 2HW plus shear stress in the wall times LW times 2, this will become a minus, is equal to 0. And from here we can find a relation between tau wall and P prime, which is equal to P2 minus P1 divided by L. And you will see we get the same relation which we get from the differential flow analysis. So things all match. Now let us look at another thing. This was the flow which we looked at. This is also called the flow between two plates, is also called a 2D channel flow. Now the case which we looked at was when the flow was caused by pressure gradient. And here the boundary conditions, now what I'm going to do is, let me shift the coordinates. Let me call this plate as H and let me place the coordinates at the bottom of the plate. And the reason, it's just, you can do it with the other one also, but let's do it this way. So flow, when flow is caused by pressure gradient, then what we get is that the boundary conditions we use is at y is equal to 0 and y is equal to h, Vx is equal to 0. And this flow which we have done is referred to in the fluid mechanics literature as Poisuelle flow. Now the flow could also be induced by movement of the plates. And as a general case, we could consider, let's say, the bottom plate is fixed and the top plate moves with V is equal to capital UI. And let us say the pressure gradient, pressure P1 is equal to P2, which means P prime is equal to 0. In this case, when you solve the equation, you will get velocity profile will take the form AY plus B. The quadratic term which came because of P prime will be 0. So therefore velocity profile in these two, between these two plates, will be linear. That means here the flow will be something like this. And this you can work out for the, and that's why I chose y is equal to 0 for the bottom plate. If that is so, then velocity profile will become equal to y times capital U by h. That is what we will get. B will become 0 and the top fall boundary condition will give us this. And this flow is called Couette flow. And this is basically, it's also sometimes referred to as shear driven flow, which is a flow caused by shear. This flow, as you realize, is not caused by the pressure gradient, but you could also have mixed flow, that is both shear and pressure gradient. And there could be different combinations. You could even get a combination where the pressure gradient, let's say, is negative, shear is positive, such that at one section overall the flow rate is zero. So that means the velocity will be basically moving in the forward direction for some part of the channel and in the backward direction for the other part, so as to satisfy the boundary conditions on pressure as well as shear. So this could also happen. Now, one thing I would like to tell you, if you realize at the start of the course, we talked of some viscometry problems, and where we had, let's say, flow between two rotating cylinders, and let's say this one was fixed and the other was moving with omega r. Now here we said that since, let's say, this delta is equal to gap, and we use the argument since the gap is thin, we assume a linear velocity profile. Well, if we look in the detail of this argument, what we were saying was that since gap is thin, the circular part can be assumed to be a straight part. But for velocity profile to be linear, a Couette flow or shear driven flow also has to be there. That means no pressure gradient to drive the flow. If we have even a very thin channel and flow is driven by a pressure gradient, then even in this thin channel, where gap is small, the velocity profile will be what? It will be parabolic and not linear. So therefore, the argument which we made in these problems of viscometry at the start of the course, that the gap is thin and there is a linear velocity profile, also assumes that the flow is caused only by shear. It is not caused by this any pressure, particularly pressure gradient. Okay. Let us look at one more problem, and this time we will look at a problem of exact solution with cylindrical coordinates. And I will not do this problem in full details. I'll just go through the basic equations and tell you how this is to be done. So let's look at a problem which is a problem of flow between two concentric rotating cylinders. So we have these two cylinders, the cylinder with, so here this is the Z direction, this is the R direction, this radius is R1, the outer radius is R2, and we have given, so let's now specify the problem. So we are talking of flow between two long cylinders of radii R1 and R2 respectively. The inner cylinder rotates with an angular velocity omega 1. Now, the outer cylinder could also rotate, and maybe you can think of this. Here we will consider the outer cylinder as fixed. Let's show this. The outer cylinder is fixed and this inner cylinder is rotating with omega 1. Now it's given as a part of this problem statement that Vz is equal to 0, and we've been also asked to neglect gravity. Well, you'll realize if we do not neglect gravity, then it will just show up with Vz being 0 only as a pressure term. So basically here you could have also said that we have used the trick that gravity has been merged with the pressure term. And we have used this, we define script P as P plus rho gz, and then we will get the same equations. Okay. Now, as a part of the this thing problem, we also specify that it is steady flow with velocity and pressure not functions of time. And then we also specify that this is axisymmetric flow. If you look at the flow, there is nothing which should change with theta. And we also say that pressure distribution in this case is also axisymmetric. Now the logic for this is that if we have neglected gravity anyway in this problem, but if gravity is vertical, then pressure, there is no component of gravity in the theta direction, so therefore pressure will not depend on theta. And then we also specify that since the cylinder is long, now this again comes, now there is no question of a fully developed flow in the z direction, but since this cylinder is long, so that means z direction can be considered as infinity. So z direction can be considered as infinity, and this will imply that partial v by partial z is equal to 0. So this is all what has been given to us. Okay, so we start solving this problem. Let's just first again look at this problem, look at the geometry. Two cylinders, there's basically fluid is in between these two cylinders. The inner cylinder may be considered to be of a solid cylinder. And so now let's try to, and let's start with the boundary conditions. So in the boundary conditions are given to us at r is equal to r1 and r is equal to r2. At r is equal to r1, what is the velocity? And from no slip boundary condition, what we get is velocity will be equal to r1 omega 1 e theta. There is no z component of velocity, there is no r component of velocity. So therefore, this is what we get for velocity. And at r is equal to r2, since the outer cylinder is fixed, we get all components er, e theta, ez, all components are 0. Now notice this is one of the problems where the problem is axisymmetric, but v theta is not 0. Okay. In fact, that will turn out to be the main this thing. So here, if I put it in scalar components, I will get VR, V theta, Vz are equal to 0. And here we'll get VR is equal to 0, Vz is equal to 0, and V theta is equal to R1 omega 1. Now we start solving the problem after reducing the boundary condition. First we go to the continuity equation. Continuity equation tells us 1 over r d by dr of r Vr plus 1 over r d by d theta of r V theta plus partial Vz by partial z is equal to 0. Now we have written the continuity equation, but if we now try to look at the velocity components which we have, Vz is 0, so we have Vr and V theta. These are the two velocity components which as of now are not 0. And they are functions of which variables? So these are functions of r. Why? Because it's given to us that velocity is not a function of z, and because the flow is axisymmetric, so velocity and pressure do not depend upon theta. And because the flow is steady, they do not depend on time. So basically when we start off the problem, velocity, we have Vr as a function of r theta z t, and V theta is also a function of r theta z t, but because of these arguments, theta it's not a function because of axisymmetry, and z is given to us long cylinder, t because of steady flow. So we use these arguments to make this, and pressure will be equal to pressure. In this case, we have only r, because theta, again, theta z t. So theta z t are specified in the problem. Pressure is not a function of these. So now we look at the continuity equation. Let's simplify this. So partial Vz by partial z is 0 because Vz is 0, and partial by partial theta of r V theta is 0 because of axisymmetry. V theta is not 0. So therefore from here what we get is 1 over r d by dr of r Vr is equal to 0, and from here we get r Vr is equal to constant, and Vr is equal to, let's call it k. So Vr is equal to k by r. Now we use the boundary condition. At r is equal to r1 or r2, Vr is equal to 0, and this will give us k is equal to 0. So from here what we get is Vr is also 0 for all r. So that means we are left with only V theta and we are left with pressure. So now to obtain the equation for V theta, let us look at the Navier-Stokes equations. Now as we have said, we first go to those components which we know are straightforward. So first we go to the Navier-Stokes equation in the r direction and z direction. Z direction, the way it is specified, we will get 0 is equal to 0. When we apply the equation in the r direction, we get, if you look at all the terms and you simplify it, now this I am not specifying each of these terms, but this is what will give you minus rho v theta square upon r is equal to minus dp upon dr. Now notice we cannot integrate this equation like this. Many times students make this mistake that they integrate the r equation as dp by dr is equal to rho v theta square upon r, and then they say p is equal to rho v theta square log of r plus constant. Now this is erroneous. This is wrong. And why? Because v theta is a function of r. So we cannot solve for pressure till we solve for v theta. So therefore then we go to the theta equation. And the v theta equation, if you look at it, you will get 0 is equal to mu times partial by partial r 1 over r d by dr of r v theta. When you look at the v theta equation, everything else becomes 0 except one term in the viscous equation. So now this can be equated. The partials can be converted to the total derivatives, and therefore what we get is the first simple d by dr of 1 over r d by dr of r v theta is equal to 0. So therefore we get 1 over r d by dr r v theta is equal to k1. So from here we get d by dr of r v theta is equal to k1 times r. And then we integrate this. So therefore we get r v theta is equal to k1 times r square by 2 plus k2. And from here we get v theta is equal to k1 prime r plus k2 by r, where k1 prime, since it's an unknown constant, we call k1 by 2 as k1 prime, or we can even call it k1. So this is what we get. And now we can use the boundary conditions. At r is equal to r1, v theta is equal to omega 1 r1 or omega r1, and r is equal to r2, v theta is equal to 0, and from here we can get the value of k1 prime and k2 prime and k2. So this is what we will use, and we will solve them, and I will leave this for you to work out. But now suppose if one has to find the torque on the inner cylinder or the outer cylinder, which is needed for this motion. Then how will you do this? So what you'll have to do is, let's say we want to find the torque on the inner cylinder. So we take an elemental area here. So which element is this? This is the when I look at the normal is in the r direction. So this is the r phase. And the torque which we are talking of is tau r theta. And for this, we look at the expression. Again, I will leave it for you. Look at the expression from the sheet. Once you have this expression, then you take tau r theta, and this will be something like, there will be mu dv theta by dr plus dvr by d theta, but there will be most likely a 1 over r, and there may be some extra terms. So you work this out, plug everything at r is equal to r1, and then tau r theta. Then if I look at a ring type of an element, of height dz. So the area of this will be 2 pi r dz multiplied by r, and we integrate this with z going from 0 to L. This will give us the total moment. But now we don't need to make any linear assumption. For tau r theta, we know the velocity profile. From there, we will be able to get the expression. And once you know the expression for v theta expression is v theta is equal to k1 prime r plus k2 by r. You feed this in dp by dr is equal to rho v theta square upon r, and you integrate this to get pressure as a function of r. And clearly it will not be rho v theta square log r, but it will be some other function which you can easily integrate and get. So this is how I've done this problem to give you an example of a problem in cylindrical coordinates. Now, next thing which I would like to do is, let's try to do an overall study of what we are seeing in Navier-Stokes equations and what we are seeing in various problems which we have solved here. The Navier-Stokes equations look like this. Rho times partial v by partial t plus v dot grad v is equal to minus grad p plus rho g plus mu del square v. This is the Navier-Stokes equations. Now let us try to see the physical meaning of each of these terms, and we'll also see it in the context of the problems we have solved. The left hand side, this gives us rho times acceleration, and this is also called the inertia term of the Navier-Stokes equation. Inertia terms, or sometimes you may use it as inertial term. So this tells us basically whether a fluid particle, so this left hand side gives us if a fluid particle in the flow is accelerating or not. And whenever this term is equal to 0, this implies acceleration of fluid particles is equal to 0. Well, from a mathematical viewpoint, we also realize that v dot grad v, this was the non-linear term. So if the left hand side, in particular, if this term turns out to be 0, the equations will become linear. If v dot grad v is equal to 0, then your equations are linear in P and V. Now, this acceleration term, that means particles, if this total term is 0, particles will not accelerate. In case of unsteady flows, in general, partial v by partial t will not be 0 and fluid particles will accelerate. Now in the exact solutions we have seen two examples flow in a channel, the circular flow between two rotating cylinders. In class, in examples in the tutorial, we saw an open channel flow down an inclined plane, and we also saw flow in a long pipe. In all these flows, and most of the flows where we get exact simple solutions, this term will be 0. Well, I made a small mistake in the rotating cylinder case. This term was not 0. The pressure was a function of rho v theta square by r. So I stand corrected there. So when this term is 0, that means particles are not accelerating. Now what about the other term? The grad P term is, it represents force due to pressure. So if the pressure causes a force, we get this term as non-zero. So grad P is not zero if force due to pressure on fluid particles is not equal to zero, and pressure is driving the flow. Also, one more thing we can realize is that this grad P term comes as gradient of P. So if we add a constant everywhere to P, grad P stays unchanged. And that is why we always talk of difference between between P at a point and some reference pressure. Because what is important, it is not the exact value of pressure, but the pressure difference which is of importance and which causes acceleration. So it's the pressure difference which causes acceleration, not a uniform pressure. Okay. So this was the grad P term. Then we have the rho g term, and this is just the body force. So let's write this term. Rho g term in the equation, this is the body force, and in general problems, if we have gravity, then g will be the acceleration due to gravity. If there is an electromagnetic force, this will also come in as a body force. This is one thing. The second thing we realize is the body force, if the body force is conservative. What do we mean by conservative force? That force can be expressed as gradient of some scalar zeta, or whatever scalar you call it. Normally we call it phi, but here we'll be using phi for something else. So if the force can be expressed as a gradient of a scalar function, so then this zeta is typically what becomes the potential energy. And what we can do is pressure and body force can be clubbed, because both have the same form, and this can be clubbed by saying, so I'm assuming this is appropriate dimension, that is it's per unit mass. So therefore then gradient of P minus grad P plus grad zeta can be written as minus gradient of some script P, and script P will be equal to P minus zeta. So we can club the body force and pressure force in some problems. But if pressure comes in the boundary condition, then we cannot club them. We have seen this earlier. Now comes the last term in the Navier-Stokes equation, the mu del square V term, and this is the viscous force term. So we have this term mu del square V. This is what we call as the viscous term, and this represents the force due to viscosity on the fluid particles. So having seen all these meanings, now there is one can also give you, let me maybe at this stage itself talk about, let's look at, for this term, if I try to see, Let's see, there's a vector identity, and the vector identity is del cross V is equal to gradient of del dot V minus del square V. So from here what you can get is that del square V is equal to gradient of del dot V minus del cross V. This is just a mathematical. So then what we will do is, if we see for incompressible flow, del dot V is equal to 0. And if in addition del cross V is also equal to 0, and we will define this in the next lecture, this term del cross V has a special meaning. If del cross V is also equal to 0, this term del cross V we will define as a vector quantity omega or vorticity. Some textbooks use a symbol Z for this, but so this is that means if flow is incompressible and if omega, which is the vorticity, not the angular velocity, if vorticity is equal to 0, then what we have is del square V is equal to 0, and in such flows the viscous term is equal to 0 even if mu is not equal to 0. So irrespective of value of mu for flows where del dot V is equal to 0, and this we know happens in incompressible flows, and at the same time del cross V is equal to 0, and this we will define this term, we'll call them irrotational flows. We have mu del square V, the viscous term is 0 in these flows. And we will look at the effects and the implications of this in the next class. So now let me just get back to the total equation. So we have inertia terms or acceleration is equal to minus grad P plus rho G plus mu D del square V. Let's try to now look at the various flows we have seen. We looked at the channel flow, which was basically, first let's look at Poisuelle flow. In Poisuelle flow, what you find is the left hand side is equal to 0, so acceleration is equal to 0. There is a grad P term, this is not equal to 0. Again, the gravity part can be clubbed with the pressure, it doesn't play much role. And we have mu del square V, this is not equal to 0. That means in Poisuelle flow what is happening is the pressure force and the viscous force balance each other. The pressure force is not causing an acceleration of the fluid particles. It is being used to balance viscosity, and this we even saw from the integral analysis of the problem, that the pressure and the viscous forces balance each other. So this is what happens in Poisuelle flow. In Couette flow, which was, so Poisuelle flow was the one where we had P1, P2, and this was the one. In Couette flow, what we have is the top fall moves, the velocity profile looks like this, and once again what we have is acceleration is 0, grad P is 0, gravity is combined with pressure, and what we have is just del square V is equal to 0. That means in this flow, it is viscosity which alone causes the flow. There is nothing else. There is only one term which is causing the flow, and that is viscosity. And so there is the top plate which is moving with velocity u. And this causes the fluid to move. Now, in general, the fluid would accelerate because of movement of the plate. But this acceleration, moving force, this does not accelerate because of viscosity. So this top plate moving would have otherwise led to an acceleration, but due to viscous forces, the fluid particles do not accelerate. Now next, let's look at the example which we have done in the tutorial class. There's a third example which we have done, and that is flow down an incline. And here we had liquid or water, and we had air on the top. So in this again, when we look at it, the left hand side of the Navier-Stokes equation was equal to 0. In the right hand side, what we got was partial P by partial X was 0, and partial P by partial Y was equal to rho times the gravity in the Y direction. So this was basically like the hydrostatic effect. In the Y direction, the gravity component basically takes care of the pressure difference. Now, what happens to, there's an X component of gravity which is not equal to 0. And this X component of gravity, basically, then we have the viscous terms, so they balance each other. The X component of gravity and the viscous terms balance each other. So from a physics viewpoint, that is what is happening in this problem. And if you recall, this X was like this, Y was like this. So gravity had both X and Y components. But once again, we notice here, even though the flow is down the incline, fluid particles are not accelerating. Okay. Now, just let's go back to the Navier-Stokes equations. We had rho times partial V by partial T plus V dot grad V is equal to minus grad P. And now I'm going to assume that the gravity term is consumed in the pressure term. So this includes G, or gravity is negligible. Now here we see that left hand side we have the inertia terms. So in this equation we have three terms inertia terms, pressure term, and the viscous term. And in general, in most problems, what happens is the scaling of the pressure term is unknown and is determined by the problem. Unless we have a problem where pressure itself has been specified, which is causing the flow, like in Poisuelle flow. But otherwise, in a lot of problems, the scaling of the pressure term is not known. And in a few lectures from now, we will be coming to this term called non-dimensionalization of the equation. And there we will show that there are some flows where inertia terms are small and can be neglected. The conditions for these we will do when we do the non-dimensionalization. These flows are called creeping flows. And in these flows what we have is grad P is equal to mu times del square V. Pressure and viscous forces balance. And this we have seen even in the exact solution. This happens at many times. But what we are going to focus on in the next few lectures will be the cases where the viscous term is small. So this would be case B, that would be case A. So the case B will be cases where viscous term is very small, which means mu del square V is nearly equal to 0. Well, we have discussed one case where mu del square V is exactly 0 when we have incompressible irrotational flow, but we will discuss these cases where, and these flows are what we will call as inviscid flows, which means flows where effect of viscosity is very small or negligible. And in these flows what you will find is that the inertia term and the pressure term, and maybe the gravity term if that is important, these terms balance each other. Now in terms of linearity and non-linearity of equations, what do we see? If we look at velocity and pressure together as our dependent variables, then what we will find is in flows of type A, which are creeping flows, the equations will be linear because the non-linear terms, the acceleration is being neglected. But in flows of type B, which are inviscid, then where both V and P are dependent variables, the equations will be expected to be non-linear. So we will continue from here in the next class, where what we will do is we will look in details in inviscid flows, and in particularly we will look at irrotational flows, and we will see what form of the equations do things take. But you may get a feeling when we talk of inviscid flows or irrotational flows, is there any equation which comes to our mind? Think about it, and when we have done integral flow analysis, the equation which we talk where we use inviscid assumption, and also we said when the flow is irrotational, this is valid between any 2 points in the flow was the Bernoulli equation. And that we will show that Bernoulli equation directly comes from the momentum equation when we look at the equation with these assumptions. Thank you.